Welcome to Spring LIB.
So we are asked to find K for this equation here. And we're given an equation that it's a reduction equation, and we're given the standard reduction potential. So how are we going to find K for one equation when we're given data about another? Well, if you have a redox situation, you can always add the reduction and oxidation potentials together, and that will give you E0 for the overall reaction. So if there's a reaction that we could add to this one, add it together, cancel out things that are on both sides, and then add the reduction and oxidation potentials, we could get E0 for the reaction. And from there, we can get K. And that's where we use delta G, which is kind of lives in the middle between those things, allows us to calculate back and forth. So if we look at table 18.1, we need to do something to get aluminum 3 plus in the equation because it's missing from, there's no aluminum 3 plus in this equation. So we need to find something with aluminum 3 plus. Well, in table 18.1, we have the equation and potential for the reduction of aluminum 3 plus. So now, if we add these two reactions together as is, things are not on the right side. So what we could do is flip the first equation around and turn it into oxidation. When we do that, our E0 flips. So that would be, it flips the sign, so that would be 2.07. So if we add these together, things cancel out, the electrons cancel, the aluminum cancels, and we're left with the equation we need to find K for, which is great. So what we just do is add the oxidation. So this has become E oxidation, and this is E reduction. So when we add them together, we get 0.41 volts. And so now we can use E0 to get delta G. So delta G is equal to negative RT ln K. Actually, we don't even really need to calculate delta G, but in this, I did calculate delta G, but you don't necessarily need to because these equations equal each other. But in any event, if we use negative NFE0, it's 3 moles. 3 moles of electrons. If you look back to the equation, there were 3 moles of electrons. Faraday's constant, E0 is 0.41. Remember that volts is equal to joules per coulomb, so you cancel everything out except joules. This is equal to negative 118.7 kilojoules. I'm setting that equal to negative RT ln K. We solve for the natural log of K, and then we take E and we raise it to both sides. That'll cancel out that natural log, and we're left with E to the 47.9, which is 6.35 times 10 to the 20. You could actually just set RT ln K equal to negative NF E0 and solve for K as well. It would be NF E0 over RT, and then so you actually don't have to calculate delta G. You can just set these equations equal. Either way will work.